Okay, so we're going to start today's discussion. We're going to enter a very interesting topic, which is, as I said, this is the core of semiconductor. We'll see the structure in bipolar junction transistor circuits or MOSFET circuits, even though in most of the MOSFET circuits, we will assume that these junctions are not forward biased. So we're going to talk about the key. We already, in our previous lecture, we already introduced the idea of doping in semiconductor in order to create N-type and P-type semiconductors. So in these two types of, this different type of semiconductor will then create a density imbalance of electrons and holes, meaning that you may, for N-type semiconductors, you will have a lot more electrons. For P-type semiconductor, there will be a lot more holes. So the imbalance in this, the other key important things we mentioned is that once you have these imbalance in carriers, you have, we call the non-uniform distribution of carrier distribution. These non-uniform distribution will then lead to forces such as drift, and drift will then lead to other things, diffusion forces will then lead to other, we're going to talk about that. There will be a balance between drift and diffusion in the p-n junction. So therefore, the forces which will govern the motion of these carriers will then lead to a very, I would say, special junction dynamic, which would allow a balanced state in a p-n junction. So we're going to talk about that. So the key parameters or key takeaway in the discussion of p-n junction are these three. First, there's something called the built-in potential. This is something that's been caused by we're going to talk about that. This will be, the built-in potential is actually created to balance. This is the result of the balance of drift and diffusion. I should say diffusion force and drift. So it's sort of like in the natural world, it will balance itself on its own. So it's a balanced state once you have these two materials placed close by, creating a junction. So at this particular location, it will then create a particular region, which is called the p-n junction, and lead to the balance between drift and, diffusion and drift forces. So we're going to talk about how much is the barrier. This is called a built-in potential, or you can view it as a barrier potential. If you look at the word barrier, barrier means that it's a blockage of flow of current. So because we have this forces of diffusion, it will automatically generate a barrier so that will prevent the further diffusion of carriers. Therefore, you reach a balance. So this is the balanced state and naturally occur to create a natural barrier which will allow the balance between balance of the drift forces. So we're going to talk about that a little bit. And then the next thing we're going to talk about is then in this particular balanced state, the next thing happens is that if you interfere this balanced state, meaning by adding external biasing. So these are the bias conditions, meaning that if this is my p-n structure, there's a junction. This is the junction area. So there's a particular junction area. We're going to discuss how it creates this balanced state. And then this is the circuit symbol. This is typically referred to as the circuit symbol of a diode, of a p-n junction. So in the circuit symbol, we will then label the direction of the voltage is being applied. So this is the external force that's being applied. It's typically in the form of voltages. So you apply something across this junction. It's called the diode biasing current. So this is a biasing condition. You either add positive bias or negative bias. So if VD is positive, we call it forward bias. If VD is negative, it's generally referred to as reverse bias. So this is the P side. You always start with the P side. So this is the P side. This is the N side. So N side will be referred to as the positive side. If you apply a positive voltage, you're disturbing the balance. And once it's being disturbed, you either, in forward bias condition, what is being essentially happen within this barrier, within this junction, is that lowers, physically what happened is that it lowers the barrier. Remember, we have a potential barrier that's been initially built by this natural setting. So what happened is that if you apply interference by applying more positive voltage on the P side, you lower the barriers, so then you allow currents to flow. So you then have current flow. So the basic idea is that, okay? So this is like if you're into politics in America, they build the wall, right? Across the Mexican border. So what happened is that if Trump is in office, what happened is this, reverse bias. So this is Republicans. What they do is that if you apply a reverse bias, meaning that you increase, I should say higher, so you build a higher wall, so to speak. So you increase the wall, which means that it will block the current flow. So what happened is that you block the flow of immigrants. This is the same thing. You block the current flow. So by adding on to the natural border, what happened is that you block current flowing. If Democrats is in office, what they do is that they lower the barrier, they tear down the walls, make it more easily for current to flow over. So this is the direction of current, why it happens, and then we can talk about how this natural boundary has been built and why does this applied voltage increase the blockage of current flow. Okay? So first of all, let's think about p-n junction diodes in terms of structure. So I wanted to draw a few graphs in one. Let me think about this. So what happened is that if I look at a cross-sectional view of my diode, it will be something similar to this. One of the key location is where it meets. So it's the interface, or we refer to as the junction. So let's say if I have a junction right in the middle, I want to define it with a dimension. So let's say if I'm using a two-dimensional device, this is the N-type, this is the P-type. And along this axis is x equals to 0. So this is just to say, this is just to note that the junction, we have a junction along this dimension, which is x at x equals to 0. Okay, so along this line, so this is the x is positive along this line. So we're going to do a few graphs. I'll see if it fits into this page, but it will be slightly more difficult. So what happened is that if you, within this exact physical junction, there's a space, there's sort of like a zone, which is like a no-fly zone or something. There's a zone in between this junction. There's a small zone. There's certain change within this particular junction. Junction area extended out to both the N side and P side, which will be a, sort of like a gray region between these two area. So if it's out of this zone, it will be a normal. It will look like it's normal behavior. It's more like the. I should say, it's more like its original behavior. So if you look at out of the border zone, what happened is that you could actually highlight your carrier concentration. So if the left side is N-type, what can be done is that you could actually highlight your electron. I could actually highlight my, if I want to draw my electron density profile along this junction, because this is N-type, there's a high doping concentration. Nn equals to Nd. Depending on how much dopant I put in, it will give me a level. And then right side, it will be Np, right? It's away from the border, so it's like a normal country. Okay. And if I want to draw the P, so if I give you a P, and PP will equals to the doping concentration at P side. And because of this, I should be able to find out this is the Ni squared divided by Na. Okay, so I can find these level out. On the left side, of course, I will also have a Pn, minority carrier concentration, which is Ni squared divided by Nd. Okay? Is good? So if I plot it this way, can you tell me which side is dope more heavier? This is a relative level. So which side is more heavily doped, or Na or Nd, which is larger? Can you tell? Nd. Okay, so the one of the way to look at it is that, of course, this is the Na. I plot Na over Nd, but you see the gap. If you have higher doping, which means that your majority carrier will be much higher, minority carrier will be much lower if it's more heavily doped. So the difference between doping levels, the majority and minority carrier will be actually wider if you simply look at this plot. So we know that in this setting, I'm setting in the slightly larger than Na in this setting. Okay? So what happened is that, I don't think I have enough space for this. So if you think about this setting, what happened is that if I'm an electron on the N side, what I see is that there's very few electrons in the P side. So if I'm just gradually gonna continue and connect the dots, just whatever it is, doesn't really matter. It looks something like this. So you assume that what happened in the border looks something like this. So this means that inside this transition period, I actually have a fairly high dndx. This diffusion force will then push, this gradients will then push electrons to go to the right. So what happened is that this is without any bias, so we can assume that this is at no bias, or you could refer to as Vd equals to 0. There's no bias between the two. Under this particular condition, the first observation is that there's a diffusion force. Pushes electrons to the right, because you see the gradients. Therefore, electrons would tend to move to the right. So if there's an electron here, it will then be forced by diffusion force to push to the right. And you also look at holes, because there's a lot less holes on the left side, on the inside, therefore holes will be pushed to the left by diffusion force. So you start with diffusion force because of the large gradients. Remember, the main reason why you want to diffuse over there is because there's less people, there's less population. Okay? So diffusion force first pushes electrons to the right and pushes hole to the left in the opposite direction. Okay? So once, if you think about it, if there's an electron is being crossed over to the other side, what is being left here? What happened is that you would then have something called the depletion region. Let me try to. So what happened is that if you, let me redraw this plot. I want to use this positive. Okay, so if you think of your silicon structure and on the N side, it will look something like this. I'm just going to draw it on the inside, it will look something like this. And arsenic inside in here. So within this range, what happened is that if this electron leave the whole region, leave this region all the way to the right, so then there will be As plus, ionized impurity. So once this electron leave the whole region, all of them is being left because there's a lot less being pushed by this diffusion force. What happened is that there will be no electron within this region. So that will cause something called it will lead to once electron and holes leave. So at the borders, once the electrons and holes leave the borders, it will leave something called a depletion. It's called the depletion region. So there will be no carriers because the carriers will tend to move over to the other side. So once these carriers left, what happened is that this would then become the ionized impurity. It will then lead to, we call this space charge. Contains of ionized impurity. So these ionized impurities are bound. Remember, these arsenic, even though it contains charge, but it cannot move, it's being bounded. The other four covalence bound. Therefore, it's immobile. So it's typically referred to as space charge or depletion charge. And its main characteristic is that it cannot move, even under field, right? Because it's bounded. So once you have this depletion charge created, one of the problem, let me redraw this again. So once again, this is x equals to 0. So then once the electron's being pulled away, what happened is that we already recognize that in this border region, there's a border region, which will then form, we call the depletion region. So there will be positive charge. These are space charge. Each one of them are, in this case, are As plus. ionized impurity. Okay? And this also happened on the other side. Once the hole left, which implies that all the borons are accepting another electron. So this will be negatively charged. So each of them contain a boron minus. Okay? Is it good? So again, this n side, this is just connection to the external circuit. So this is the n side, this is the p side. So what happened is that once you have this charge, which is being displaced, we'll call it this. This is, as I said, this is referred to as the. This region is referred to as depletion. The reason why it's called depletion region is because it's depleted of N and P. So some of you might heard a phrase of depletion approximation, meaning that we assume that within this depletion region, we call it depletion approximation. Within here, n equals to p equals to 0. There's no electrons and no holes. Within this depletion, this is an assumption. I should say that it's an approximation, so it's approximately close to 0. So meaning that within this depletion region, you would then be governed, the amount of charge is being governed by this ionized impurity. So if I wanted to plot something like this, I'm always out of space. So if I ask you, this is x equals to 0. If I want you to plot the amount of charge, the charge density along x. So if I want to plot charge density along x, you will see something like this. This will be, it only happens within this border, which is, I'm also going to define the dimension. So this is minus xn. So how far does the border go? We define it as a depletion width. So we'll deplete both sides, and this side will be xp. So there will be three important points in dimension 0. And from the border, it will deplete to the n side and also to the p side. How long does this depletion region grow will depend on a lot of things we're going to talk about a little later. But just to bear with me on these parameters. So once we have these parameters, we can first draw what is the charge density. So there's basically three regions to remember. Within, if you cut it in three, there's zone 1. There's zone 2. There's zone 3. So in zone 1, it's neutral. This is just the typical region we have where your electrons are still with your electron has not left the region. Therefore, your n plus, I should say neutral region, which is n plus nd q. Remember, we had the charge neutral thing. Let me write it down. Plus q, p equals to 0. Let me rewrite it just to. So this is following our neutral guideline, which is minus qn, nn, equals to positive q in d plus positive q pn. So this is this equals to 0. This is our charge neutral equation in the n-type region. So this is we call the n-type neutral. This is n-type neutral region. In the second region, what happened is depletion approximation. There's no electrons and no holes. Therefore, the amount of charge, this is called the zone 2, is the depletion region. If we assume that all of the carriers being depleted, being pulled away, depletion, therefore n equals to p approximately equals to 0, therefore your charge within this region, I should say, the charge level within this region from minus n to 0 equals to q and d, positive to q and d. So your level from 0 to xp would then be minus q and a. Okay? Let me write the third part so that you know what we're talking about. So on the p-type neutral, it will be positive pp plus minus q and a plus minus q and p. pp. Sorry. Just want to make sure that I make it right. So this equals to 0 when it's neutral. Okay? So how do I get the above level? Is that when I'm assuming these two are 0, you get this. If you're assuming free carriers are 0, you get that. Okay? So this is just to say that if I'm drawing the plot, I would then have a charge region which looks something like this. It will be a charge, positive charge, at the level of q and d, and negative charge at the level of q and a, minus. Okay? Did I draw it right? Should be a little less. Not sure I'm doing it right. Okay? So in this plot, what happened is that if my ND is higher than NA, what happened is that the whole thing, even though there's a depletion region at this particular border, what happened is that it was then, the whole thing should be a charge neutral. If I wrap the whole junction up, the net charge should be 0. Otherwise, there will be potential gradients along this line, along this neutral region. Therefore, this simply means that the area highlighted in blue will be identical to the, let me use a different color. I'm using green, right? So I'm just going to use green, just to be consistent. So this will be minus, the level itself will be minus q in A. Okay? So simply imply that this area, the total net charge in the P side should be identical to the N side. It should then balance itself so that for charge neutral of the whole system, whole device, you should be aware that QND plus XN, that's the area, plus minus Q NA plus XP, this two should sum up to 0. That means that net charge is very, very important results, which would imply that if I'm having a higher doping, then my depletion will be narrower on this side, and it will be thicker on the other side with a lighter doping. Okay? This will simply give you a very interesting result, is that your ND they're inverse proportional to their doping level. The depletion width, we call it depletion width. Xn are depletion width to the N side, Xp is the depletion width to the P side. It will then depend on its doping level. The higher it goes, the higher the doping, the less depletion because of the area. Should balance out itself. Okay? So next observation is that once we know that there's a depletion region at this border region, at this border side, what happened is the third observation, I want to write down the third observation, is that because I have the displacement in charge, meaning that there should be an electric field, right? Because the charge is not aligned. It's not charge neutral at all locations. At the depletion region, you will then have net amount of charge. If you're looking at this particular border, you will see that it will create an electric field. So these charges will then create, we call it built-in electric field. So what's the direction of the electric field? If you think about it, it will be there's an electric field in this direction, in the positive direction, right? So this electric field, you would then have electric field in X positive direction, which would then pull electron to the minus X direction, pull holes to the X direction. Okay? So if you look at this conclusion, it's balancing out as the initial drive of the pushes. So let me do some little summarize on this. What happened is that if you have a p-n junction, first of all, you would experience a force, diffusion force, because of the great imbalance in concentration. Therefore, electron tries to move to the p side, hole tries to move to the n side. But once it starts moving, what happens is that at this border, you will then create, we call it depletion region, because once these electrons leave the n side, it will leave ionized impurity, positive ionized impurity. And on the p side, it will then leave negative ionized impurities. So these ionized impurities would then create something we call the depletion region, and then generate a building potential, and then pull the electron and holes back to its original places. So these two forces would then balance itself and then create a natural border, a natural barrier. So let's look at how does one build up this natural how does one calculate this natural barrier? See, if you look at this, the other drawing we typically would like to draw here is, I actually have two more, so see if it will fit. So the next thing we want to draw is, of course, if you want to understand what happened at the border, the next thing we want to draw is what is the electric field? This is the charge distribution. We want to draw E as a function of X. So can anyone tell me where's the highest electric field happens? What do you think? Everyone takes electromagnetic courses, right? 电磁学，电磁学，你修过电磁学举手？都不敢举啊。 正在修，刚开始修吗 ？OK， 没有人已经修过的吗？修过举手。Does anyone know what the Gauss law is？ 高斯定律有吧？国中还是高中？高斯定律说什么？那会等于里面的，对 ，Yeah, correct。所以呢，我稍微重复一下，如果有人不知道什么是高斯定律 ，but 高斯定律就是 if you do a integration, if you created a sphere which will surround, you integrate all the electric field, and then it will then equals to whatever charge is being surrounded or wrapped around this Gauss surface. So we can actually do the same thing. Just to refer to as the amount of charge will then be maximum. The electric field will be directly proportional to the amount of charge being surrounded by this Gauss surface. So if you assuming that you have a Gauss sphere, a half sphere coming from this side, and it moves all the way to the left. So if I'm moving from the right side, there's no charge. The net charge on the right is 0. The net charge on the left is 0 because these two sum up to be 0. So if I'm moving this surface slightly toward this edge, you're assuming that in this neutral region you will have 0 electric field. So I'm drawing electric field. In neutral, there's no charge. The net charge is 0 if you wrap it on the left or wrap it on the right. So it should be 0. It will only create electric field within this depletion region. So once I'm starting to move the surface, if you think about it, the net amount of charge will be this. So we'll actually increase linearly with the amount of charge it increased at each location. So I'm not gonna do the derivation just to show you what it looks like. It will look something like this. It will peak at the interface. This is the location where you have the peak amount of charge being surrounded. Okay? And then it will start decay again because the net charge will be canceled. Right? If you consider your surface moving from the right to the left. So this will be the distribution of electric field along the junction. So once we know the amount of electric field under the junction, the next thing you can do is to find out the potential. So what is the relationship between potential and electric field? What do you do? We know that E, let me get it back. We know that electric field equals to minus dV dx. So that simply means that d minus dV is electric field. I should say minus electric field. So your potential will be electric field. You integrate over a particular region, integrate the region across. So you do an integral and find out the potential. So let me just draw the final results. So because there's a minus sign, so the integral should be the area under this. So the area, if you integrate the area under this, you would then get the potential difference. And it will be higher on the N side, lower on the P side because of the minus sign. So if I'm trying to draw the potential, V as a function of X, it will be, what color is being left? So in the neutral region, it will be flat again. And once there's electric field, it will start changing. Integral, and then it will flatten out when it's closer to the edge again. So the difference between the two, there's a height, is then our built-in potential. So we're going to get to how you find this level, but you will see that there will be a built-in potential that's being built by integrating the electric field created by the depletion region. Okay? So is everyone following me? Or is it's good? Any questions anyone wants to bring up? I'm not moving too fast, right? Okay? So what we're going to do, let me do the derivation first, and then we'll come back and then just to give it more intuitive thoughts onto what happened at a PN junction. So one of the key important idea you need to understand is that the reason why we have this natural buildup of barrier, this is a barrier. The way to look at it as a barrier is that if you look at an electron, for an electron, lower potential is looking in the inverse direction. For electron, it will be a barrier of this height. For a hole on the right, so for electron here, is looking in the inverse direction, therefore you will see a barrier. For a hole on the left, on the right, you of course see a barrier. So for electron trying to move, you will see a potential barrier, which is VO. So it's the same type of barrier, same height, same amount of barrier, which block the further diffusion of electrons and holes. So the reason why this it reaches a particular balance is that the two forces balance itself. So at the initial, if you think about it, initially if I place the N and P together, the diffusion happens and the depletion region started to grow. And at a particular point, it will then stop growing and reach a stable equilibrium state, which will then be the balance between the two. So if you think about it, at let's write it slowly, at equilibrium, and an equilibrium state, you assume that your drift and diffusion forces for both N and P are 0. So we know that the drift current, the diffusion current is balanced by the drift force. And this should be true for both N and P's because there's no recombination. We're not assuming any recombination of carriers. Therefore, each of the carriers has to balance itself. Okay? Both of them should balance itself on its own. So if I place an electron within the system, the two forces should balance itself so that the electron, the net current flow will be 0. Okay? So you can consider either holes or electrons. Here, my example, if I'm consider a hole, consider hole current, the balance of hole current in depletion region. We're going to do a little math, and then we'll come back to explain what it means. So if you use the bottom equation, you can use both equation 1 or 2. It's the same. It will give you the same results. So I'm doing the second one. I'm doing equation 2. You can do the exercise on equation 1, and the results should be the same. So it tells us that my drift hole current plus, it doesn't matter which one you write first, should equal to 0. So what is in the front? The drift, you go back to the drift current equation, is mu P mu p electric field plus what is the there's a minus sign in its diffusion current. Remember, because the diffusion direction is inverse of the gradients. So this equals to 0. So what we're going to do is actually change this into this. The electric field is equals to minus dV dx. Okay? So then, and you get rid of the q's. So this would become minus mu p dV dx. The minus signs come from this minus sign. And there's another minus sign, minus dp dx equals to 0. And I'm going to rearrange my equation into minus mu pp dV equals to, okay? So I'm getting rid of the dx, and timing dx on both sides. So this will be the equation. We're going to do what? We're going to find out built-in potential V0. So how do you do that? You do an integral. You do an integration. You find out the integral of potentials along this changes. But we're not going to integral against voltage. We're going to integral against carrier concentration, because this links to each other. So then you can rewrite my equation. The equation can be rewritten as minus p. If I'm integrating from minus n to p, minus xn to xp, this is within the depletion region, the boundary dV. So the right-hand side, I'm moving the p over. And this will, on the left-hand side, it will be p. And because the p is integral into the right side of the equation, will be 1 over p dp. So this is just algebra. What you do is that you move the p over and integral the left side. Okay? So this would simply be voltage at xp minus voltage at xn, because all of them are independent of voltage. So you just pick the 2 points, and this will be dp ln. Sorry, I forgot to label it. This will be p at xp. This will be p at xn. So give the boundary condition. Let me highlight the boundary condition. So we integrated from the left side of the p-n junction to the right. And so therefore you look for the whole concentration on the edge of the p-n junction from the left to the right. To be more precise, this should be minus xn. Okay? Okay, so this will then become, so what we need to do is to find out what is the whole concentration. You go back to this plot. This is xn minus xn. This is xp. So what is the whole concentration at xp? I'm trying to p at xp equals to pp, the majority carrier concentration, right? So we're also interested at finding out whole concentration at the edge of this. At the edge, we know that it's Pn. Okay? So I can change this into pp, majority carrier concentration. This is minority carrier concentration, both whole concentration, but one as majority, one as minority, because it's at the two sides of the border. So then this will be ln p minus ln pp. Sorry. Okay? I still have a minus, yes. So this is V xp minus Vxn will then become, there's a minus sign of mu p ln p p pn. Okay? And because we know that your voltage is actually higher on the N side, therefore your VO, our building potential VO, is defined as the, I'm sorry, I forgot the minus sign. So at the two border, VO is defined as the higher voltage at the N side minus the lower voltage at the P side. So therefore, you get rid of the sign. Just to make sure that I didn't make any mistake. Give me 2 minutes. So there should be P. Diffusivity. So the next, I'm just going to, 2 more steps. So what is this? You still remember? Einstein relation tells us that it equals to kT over Q, which is the thermal energy. So let me use a red to emphasize. So your building potential will then be proportional to kT over Q. And what is this? PP. PP is, according to this, is Na, and Pn is this. So you will then be this will be a very perfect equation. This will be Na. My minority carrier concentration will be determined by the other side. Okay? So finally, I'm just going to give the punchline of this course, of this hour. I don't know if I write it in red. Is it more clear or not as clear? Okay, so this is the first part. We're trying to hit the point is that what is its building potential? And its building potential is being constructed to prevent further diffusion, to counter diffusion force. You can see that counter gradient difference. Therefore, the gradient is the larger the difference between the concentration on the right and the left, the same type, will be this. This will be also true if you do the same derivation by using the N. You actually get something. This will be equals to dN mu n ln nn P. I will explain why I'm writing that down. If you do it with N type, you actually come from the other side. But the results will be the same, identical. Right? Because this is, what is this? This is ND. This is Ni squared divided by Na. So you flip it, and it will be the same. Okay? So let's take a break for 10. We'll come back in 15 past 11, and then we'll continue on giving you more insight into how to read this results and what does it imply.